Hello, everyone. Welcome to another wonderful day of chemistry. So today we're going to go ahead and continue our conversation about acids and bases by looking at how we can talk about how strong an acid is versus how strong a base is and how these two are related. And as a hint, it comes down to pKa. And no, I am not speaking in Pokemon. So when we're trying to look at the acidity of a solution, one of the classic ways is we just look at the number of protons. But another way we can do is look at the actual acid itself. Is it a strong acid or is it a weak acid? And we've kind of seen this already. We do this by looking at how an acid reacts with water. And what we're going to do is look exclusively at the likelihood of that acid disassociating to release hydronium or protons. And this reaction is called the acid dissociation reaction. So one of the big metrics for trying to figure out how favorable this reaction is, surprise, surprise, our good old friend, the equilibrium constant. However, it turns out that acids are such an important reaction, they have their own special type of K, just like we saw with Henry's. This one is called the acid dissociation constant. Yeah, we're ever so clever. And all it is the equilibrium reaction for an acid falling apart in water. Now, one of the big things to note, water does not show up in our equilibrium constant, so it's just going to be the concentration of the conjugate base times the proton concentration over the amount of weak acid present at equilibrium. Now, when we're looking at these acid-base reactions, they fall into two major categories. The first of which is our good old friend, the strong acids. So what makes a strong acid is that they have a Ka that's greater than 1. It means that they're product favored and they're more likely to fall apart into protons than they are to stay intact as that acid. So let's say I'm looking at something like HCl, one of our quintessential strong acids. Well, it turns out to have an equilibrium constant somewhere around 2 times 10 to the 6 10 to the 6. So this is actually fairly strong acid. Again, when we're looking at a lot of our behaviors, this is the sort of point where we can start ignoring the quadratic equation because it's going to fall. There's going to be very little of my HCl left. And as a result, we're going to pretty much ignore any existence of a reactant and assume all we've got left is chloride and hydronium. On the other side, we've got the weakest of all acids, the one that barely falls apart at all, is going to be water. And we've seen this reaction before with the water dissociation reaction or water autoionization reaction, where again, water reacts with itself, forms free protons and hydroxide, and has a very low equilibrium constant. This will pretty much be the lowest Ka you'll ever see, about 10 to the negative 14th, because anything else is a worse acid than water. And water has a lot of concentration going for it. So pretty much anything else we can pretty much assume won't fall apart at all, won't act as an acid at all. So this is kind of our bottom. This is kind of our top. Most everything falls in between. So these are going to be our weak acids. So if I've got something with a equilibrium constant somewhere between 1 and 10 to the negative 14, this means it's only going to partially disassociate. Most of it will stay intact because the K is less than 1, meaning that it's reactant favored. But it's still going to be a better acid than water, and as a result, will often contribute significantly to the amount of protons present. So this will include things like acetic acid, one of our quintessential weak acids. Most of that acid will stay as the acetic acid, but it releases enough protons that it can do a number of cool reactions. We also have things like hydrogen cyanide, not nearly as good of an acid. Its equilibrium constant is 5 orders of magnitude less, so it will not disassociate. It will disassociate even less, and will release fairly few protons. So these are really going to be our weak acids, something with an equilibrium constant, probably less than 10 to the negative 1, so 0.1, but still greater than water. So one of the problems we have when we're dealing with these weak acids is that they can have equilibrium constants in between 1 and 10 to the negative 14th. As you may have seen before, if we've got that big of an difference in orders of magnitude, our go-to practice is to try and turn it into a log basis. So welcome to our good old friend P once again. So we're going to do the pKa, or the negative log of the Ka. So when we're looking at our equilibrium constants, really what we're going to be looking at is the order of magnitude that will map fairly well to our pKa. So as a result, since our Kas are between 10 to the 0 and 10 to the negative 14th, our pKas are going to be between 0 and 14, again, for most of our weak acids. Any substance that has a negative pKa will be considered a strong acid, and we'll just assume that they mostly break apart. Now, if I've got a pKa somewhere between 0 to 7, this is going to release a significant amount of protons. That said, most of the acid will stay intact, but it will contribute significantly to the pH of the solution, as we'll see later. If I've got a pH greater than 7, this is going to release a lot less protons, but as we'll see when looking at things like hydrocyanic acid, HCN, it can still make a solution fairly acidic in the right circumstances. So one of the biggest things we should always keep in mind is that every acid does produce a conjugate base. So if I'm going to end up adding just that straight base in the solution, this will also have an impact on the pH. So one of the things we're going to do in order to evaluate the strength of these bases is going to be looking at what's called the base ionization reaction. So similar to acids, we're looking at the likelihood of a base interacting with water to steal a proton, and again, releasing that hydroxide. And just like we evaluated the strength of an acid with the Ka, we're going to evaluate the strength of a base with a Kb. So this is going to be the base dissociation constant. And again, will be related to the concentration of our conjugate acid times the hydroxide over the amount of base present at equilibrium. And again, our weakest base is going to be water, Kb 10 to the negative 14th. Same as our Ka, because it's the same reaction. But we also have strong bases. So these are going to have Kb's greater than 1, meaning that they're going to generate a lot of hydroxide. Pretty much we're going to assume complete dissociation, and that all of the base we added goes straight into hydroxide. Now, similarly to the acids, our bases have a huge range of Kb's, going from 0 to 14. And as a result, we're going to evaluate their basicity by looking at pKb, or negative log of Kb. You may have noticed the trend here. And again, similarly to what we saw with acids, if I've got a small Kb, this indicates a pKb. It means I have a large Kb, because my Kb is going to be 10 to the negative pKb. So as the pKb gets larger and larger, my Kb becomes smaller and smaller, and this means that my base isn't quite as effective. So a large Kb is going to show that a base is going to be very likely to steal protons from water or any acid. We're going to make a lot of hydroxide. And if I end up having this large Kb, if I add a lot of hydroxide, well, this is going to chew up the presence of any free protons, because as we've seen with the neutralization reaction, hydroxide reacts very well with protons to make water. So as I end up having more hydroxide, I'm going to have more of a basic solution. The pH is going to go higher because there will be less protons present. So conversely, if I've got an acid with or a base with a small pKb, we're more likely to have an acidic solution. Now, let's go ahead and try and relate our acids to our bases. So one of the important things is that any acid will present a conjugate base. So we can relate the strength of my acid with the strength of its conjugate base to see if these two are related, which would make sense, because if I have a strong acid, it means I'm likely to fall apart. If I have a strong base, it means I'm likely to go in the reverse direction. So we'd expect these two to be linked. And we can observe this if we combine these two reactions. So this will end up forming the water dissociation reaction, because as we add these two reactions together, the acid ends up canceling out, and so does the conjugate base. And all I'm left with is water reacting with water to produce hydronium and hydroxide. So this is our quintessential water dissociation reaction with its K of 10 to the negative 14th. Now, what this allows for is to develop our mathematical relationship. If I add two reactions together, it means I multiply the equilibrium constants. So Ka times Kb gives me Kw. So again, multiply these two together, and they should equal 10 to the negative 14th. So as my acid becomes stronger, my Ka gets bigger. That means my Kb has to become weaker. Similarly, if I have a strong base, large Kb, my conjugate acid is going to become much weaker. So these two species are going to be very related. The acid says I want to go this way. The base says I want to go this way. They have to hit a middle ground because essentially we're just looking at forming hydronium and hydroxide in that back and forth reaction. So what this also lets us do is relate pKa and pKb. And we can observe this by combining those two equilibrium constants, and again, that water dissociation reaction, and then taking the negative log of the whole thing, so both sides. Well, the negative log of Kw is going to be fairly nice because it's negative log of 10 to the negative 14th. We've seen this one before, it's 14. But on the left-hand side, we can split the log of the product of our two equilibrium constants to the sum of these two different logs. Well, this one's going to be pKa, and this one's going to be pKb. So similarly to what we saw for pH, if I add my pKa and pKb together, ta-da, they equal 14. So again, the pKa is going to represent the strength of an acid, lower pKa, stronger acid. pKb represents the strength of the conjugate base. So smaller pKb, the stronger the base. And again, we can tie together all four of these metrics about acid and base strength in a very similar fashion to what we saw for pH and pOH. So the Ka and Kb are related as the product of these two species equals 10 to the negative 14. So you know one, you can solve for the other. And similarly with pKa and pKb. So if I want to determine the pKb and I know the acid strength, it's just going to be 14 minus that pKa gets me the pKb. Now, if I have a Ka and I want to get to the pKa, it's just going to be negative log and 10 to the negative pKa to go in reverse, which is going to be very common because for convenience, most Kas are going to be reported as pKas. Now, a little bit less commonly, you can take a pKb and turn it to a Kb, and then take the base dissociation, constant and convert it with the pKb. So using all of these metrics together, we can evaluate the strength of an acid and a base. However, next time, we're going to take a little bit closer look at what this looks like in essentially a functional form. What structurally makes a good acid and what structurally makes a good base. Until then, take care.